So let's go through a couple of these common limits that you're really going to need to know well for this next section. These are from Calc 1, and we're going to mostly use graphs to understand these limits, and essentially really horizontal asymptotes and vertical asymptotes. So in some ways, if you look at the four limits in the right-hand corner, those are all definitions of horizontal asymptotes as t goes to infinity or negative infinity, and this third one, as t goes to 0 from the right, that's actually a vertical asymptote. Hopefully I said horizontal for the others. I can't remember. I feel like I might have messed that up. So let's look at the first one, the limit of e to the t as t goes to negative infinity. So I'm going to show you how to kind of think about this in two ways. So the first way, if you know the graph, is actually probably the easiest way, but I also want you to be able to just use critical thinking skills to also do it. So if we were to graph e to the t, what would that look like? So e to the t, we all should be familiar with this graph. It kind of looks like that. And we know that it's asymptotic to the x-axis, which is y equals 0. And so when I read the limit as t goes to negative infinity, that's this side here, right? So basically t is your x-axis in this case. So as t goes to negative infinity, the function is approaching that horizontal asymptote. And so I know, without doing any really analytical thinking, from the graph that is, that the y values are going to approach 0. But you should be able to process through that as well. So that is the answer, but let's also think about it without the graph. So we're looking at the limit of e to the t, and how does e to the t act? So when we read a limit statement, that's what we're asking. E to the t acts like what? Okay, basically the y values, acts like as t goes to negative infinity. That's the question. So this is improper to write, but it can be useful to understanding. So we don't put in negative infinity. Infinity is not a number, it's a representation. But imagine what e to the negative infinity acts like. I'm going to rewrite that, okay? So e, like again, this isn't technically how you should write it, but it is useful. So e to negative infinity, we know we can rewrite negative powers as 1 over e to those positive powers. And really where I'm getting at in this case is e to the infinity, any number to infinity, as long as it's positive, right, and above 1, is going to get very big. So 1 over e to infinity is acting like 1 over a very large number. It's getting huge. And you know that 1 over a very, very large number, the larger that number gets, you're going to approach 0. So that's another way of thinking about it. So e to the t approaches y equals 0, or just 0 as t goes to negative infinity. So that's one way of thinking about it. The second one is the limit of e to the negative t as t goes to positive infinity. Now again, you can do this graphically like I did the other one. Now with e to the negative t, right, so I just want to make a point, this was y equals e to the t. When you throw the negative inside the argument, you may remember from pre-calculus that it reflects the graph about the y-axis. So if I was to graph e to the negative t, and hopefully you can do this in your head and you don't even need the calculator, you know that it reflects about the y-axis when you put the negative inside the argument. And then as t goes to positive infinity, we're looking at this direction. And again, we have that horizontal asymptote out y equals 0. And so once again, in this case, the limit's going to be 0. But let's make sure we can think through it as well. Put a line there. So e to the negative t, it's actually going to be just like the one above us, right? But as t goes to infinity. So e to the negative t will be e to the, again, we don't normally write that, but as t goes to infinity, which is 1 over e to positive infinity, which is 1 over a large number, and any number over a very large number, as that number gets bigger and bigger and bigger, it'll approach the value 0. So that is the algebraic sort of interpretation. The third one, again, I'm doing all of these hopefully, just because I want everyone to know these graphs, and you should know them. The limit of natural log of t, as t approaches 0 from the right-hand side, so if I graph this one, we all should know the graph of the natural log function. It's actually the inverse of the very first graph, the exponential, right? So if it's the inverse, you basically flip-flop your asymptotes and your points, and you get a graph that's symmetric with respect to the line y equals x. So in this case, you do have another asymptote, but that asymptote is a vertical asymptote. And technically the equation, I guess, is t equals 0 in this case, right? Because instead of x. When you see this, this is the definition of the vertical asymptote. You might remember from pre-calculus. So in this case, the function, as it approaches 0 from the right-hand side, it doesn't even approach it from the left, what is happening to your y values? Well, your y values are going through the floor, right? The y values are going to negative infinity, and that is the evaluation of that limit. It is negative infinity. So definitely know the graph of the natural log. It pops up enough, you need to know it. And again, and this is a very common limit that's used. And then the fourth one is the arctan. So I know that not all of us will know the graph of the arctan by heart, so that's why I wanted to go over it for the last one, and then I'll do another video on some other ones. So for the last one, it was the limit of arctan or inverse tan, it doesn't matter, of t. You'll notice that when we get to this section, we use t's. That's why I've changed from x's to t's here. And you may not know the graph, but what I do hope is you know the graph of the tangent function, okay? So if I asked you to graph the tangent function, you should be able to at least know that that has vertical asymptotes at x equals pi over 2, and then, you know, obviously it has infinitely many asymptotes, but you should be aware at least of this one full period here of this graph. So the tangent function looks like this, and I know it repeats itself on and on. But the arctan function is only defined between negative pi over 2 and pi over 2, not including the endpoints because they're not defined there. So for the arctan function, remember that when you're dealing with inverses, you're just flip-flopping the x and the y values. So this was pre-calculus. So if x equals negative pi over 2 is a vertical asymptote for the tangent function, then it has to be a horizontal asymptote for the inverse function, which means, oh, I'm putting pi over 2 first. Sorry, here's negative pi over 2. So both of those vertical asymptotes become horizontal. And you can see that the graph approaches the asymptotes. That's not going to change. So when I go graph the arctan, it's going to look something like this. It has to be symmetrical to the tangent function because it's its inverse. So this is the arctan or tan inverse, it doesn't matter. And you should be familiar with this one. Again, it pops up enough, I'm letting you know, be ready. Then how does this thing work? Let's go back to the actual limit statement. As t goes to infinity, well, t going to infinity is this direction here. What happens to my y values? Well, the y values approach pi over 2. Now, they don't ever hit pi over 2, but that's not what we mean by limits, right? It's what is it approaching? So make sure you've got these limits in your toolbox, and we'll go through a few others that require really just thinking and analyzing and kind of give you some help as you go through these problems. So you're not focused on these because we want you to focus on the new concept, not stuff from Calc 1.